Hi, my name is Ephraim Jincy Franco, and I'm going to discuss the first part of our study entitled Design of Solar-Powered Lightweight Building and Adaptation of Low-Impact Development in Don Honorio Ventura State University College of Engineering and Architecture Extension Building. So, 2 years ago, Don Honorio Ventura State University experienced floodings due to excessive rainwater that collected on its pavements. So, these pictures are the evidences of the scenario. The first one is in front of the main building, the second one is in front of the laboratory high school, and the last one is in front of the administration building. The occurrence that caused flooding is one of the effects of land development. So land development is the transformation of raw land into more productive and profitable local. According to Philippine Statistic Authority, since 1980s, the farmlands or the rice land of the Philippines have shrunk into 48% because of land development. Basically, since our country is growing, there are two effects of land development. The first one is the economic stability, and the second one are the environmental effects of land development. Land development aims the maximization of land for human use. So it is converted into construction-ready houses, schools, commercial, and industrial sites. The process also involves the dredging, draining, filling, and excavating of pavements. Basically, land development has two effects in our country. The first one is the economic stability, and the second one is the environmental effect. According to Philippine Reclamation Authority, there's an increasing demand for land development. More land development means more extra income and a healthy economy. On the other hand, land development has effect on our environment. According to Lubowski of 2006, land development takes over rice lands and turns them into commercial buildings, roads, subdivisions, and beneficial vicinities. According to a study of Scheck, Crossman, and Devers of 2000, habitat destruction, fragmentation, and alteration associated with urban development have been identified as leading causes of biodiversity declination and species extinctions. According to Marland of 2003, the disturbance causes the imbalance of energy in Earth's surface through the global atmospheric concentration of carbon dioxide and other principal heat-trapping gases. In line with the environmental effect of land development, we are introducing low-impact development. Low-impact development is approach to land development that uses various land planning and design practices and technology to simultaneously conserve and protect natural resource system and reduce infrastructure costs. It refers to systems and practices that use or mimic natural processes that result into infiltration, evapotranspiration, and use of stormwater. Low-impact development involves different methods such as green roof, porous pavement, bioretention, rainwater catchment system, and rain garden. As an end result, low-impact development result into land development that equalize human benefit and environmental function, leading to increased land and institution values. For our review of related literature, we have studied the book of Busby, Bhaskaran B. of 2003. In his study, it was stated that green roofs and vertical gardens has two effects. The first one is the cooling factor, and the other one, it serves as a stormwater management facility in the area. The study of Peck et al. Of 1999, it states that green roof and vertical gardens are the technology that could play a vital role in helping cities to adapt in the climate change. Being porous pavement is one of the low-impact development techniques in the study of E. A. Jerlin, L. Fowler, C. R. Carroll, and Water Research of 2006. Porous pavement has an end result of 93% infiltration and reduction of the surface runoff in the given site. On the other hand, Abiad, MP, Suidan, MT, Shuster, WD of 2010 has conducted another research of pervious pavement or the permeable pavement. It says that permeable pavement can be also a treatment for water pollution. So locally, we have a study of pooling water system in a small developing island, Cebu City, Philippines, integrated stormwater management. The OST, or the Department of Science and Technology, has created a stormwater management facility and installed it in Cebu. We have studied if low-impact development can be applied into schools. Luckily, we have found LID in use schools, the LAUSD example. So LAUSD stands for the Los Angeles Unified School District. So this school adopted low-impact development, and at the same time, the design considerations include safety concerns, accessibility requirements, fire codes and fire lanes, real estate's limitation, and cost maintenance. This shows that low-impact development can be adapted into schools. So the various methods of low-impact developments are the green roof, rain garden, permeable pavement, and rainwater catchment system. In addition to the adaptation of low-impact development, we've added the study of solar panel system. So we found out that in a case study of solar panel system at Boston College, solar panels offers both environmental and economic benefit, especially at universities where energy consumption is high. For our study area, we have chosen Don Honorio Ventura State University. So Don Honorio Ventura State University was founded on November 4, 1861 by Augustinian friar Juan P. Zita and a civic leader, Don Felino Hill. Don Honorio Ventura State University has a total land area of 79,182 square meter or approximately 8 hectares. It consists of 48 buildings. Since Don Honorio Ventura State University focused on engineering courses, the College of Engineering and Architecture covers the 3,647 square meter of the land. The College of Engineering and Architecture main building, particularly the upcoming construction of the extension building, is the focus of our study and can be the benchmark of our school.
Being a university, DAVSO accommodates thousands of students, and since the school still has been accepting a growing number of students, so as the demand of adding additional classrooms and facilities is growing. In fact, we visited and conducted an interview to the office of the plant at the physical facilities of the school, and we found out that there are a lot of proposed and under construction buildings inside the campus. And as per this situation, this just contributing to the decreasing potential infiltrating part of the ground and may cause severe flooding during rainy days, which the College of Engineering and Architecture has been experiencing. On the other hand, DAVSO also uses a non-renewable energy through the electric company Pampanga Electric Company 2 or PELCO 2. The growing number of students is also equivalent to the growing demand of energy consumption, and consequently, we all know that the excess use of non-renewable energy is very unhealthy, especially as being a natural resource, as it is not propagating itself, and also unhealthy to the people because it releases more carbon dioxide. But the continuous consumption of non-renewable energy is a real problem in terms of the stock will be gone in the period of time. And this is why we came up with this study. This study has the general objective of designing a lightweight building with high aesthetic and recreational value with an adaptation of low-impact development. Along with this objective is to design a building using load and resistance factor design. Also, to reduce surface runoff through the low-impact development using green roof and pervious pavement. And lastly, to reduce the usage of non-renewable resources by installing solar panels. The adaptation of low-impact development techniques, such as the green roof and pervious pavement, would mitigate the surface runoff and lower the risk of flooding, particularly in the flood-prone area, the College of Engineering and Architecture building, and its surroundings. Though it will not totally prevent the flood, it will just lessen the possible risk and negative outcome of the flood, such as producing waterborne diseases, which leads people getting sick and cancellation of classes. The use of green roof also reduces the ambient temperature and regulates indoor temperature that will definitely aid one of the students' struggles. And by designing the proposed building using lightweight material, which is the steel, the speed of construction may increase because of its sharp fabrication. This would help out the increasing demand of construction of additional facilities and classrooms for the fast-growing number of students. Also, the use of the steel design is more economical compared to the reinforced concrete design and contributes aesthetic appeal that the school as well as the students would benefit from it. While the use of LRFD method is a practical world-class and trusted design specification according to the Midwest Steel, having the advantage of acquiring a constant factor of safety, especially the proposed building will be primarily used by students. While the use of solar power system contributes to benefits, given that it is a renewable resource and thus accompanied by electric company, the school would benefit by lessening the expense of paying miscellaneous for electricity. Also, Bacolor, Pampanga has often experienced blackouts that distract students and their classes, which contradicts DABSU's vision and mission to provide a conducive environment, which the solar power system takes place by only needing the help of the sun to function and provide an electricity. So, the scope of our study are, number one is designing of two of the low-impact development techniques, which are the green roof and pervious pavement. These two are the only applicable techniques for the study due to location restriction. Next is the structural design, perspective view, and architectural plan of the proposed building, along with the adaptation of low-impact development and solar power system. Along with this is the use of the load and resistance factor design, or the LRFD, in designing the beams, columns, and connections. And lastly, the estimation of the expected cost of the project. We also delimit some activities due to time, location, and financial constraints, such as the production of miniature or other mode of presentation to more physically visualize the proposed study. Rather, we only provided the perspective plan. We also delimit the metal decking due to manufacturer's restriction. The design of drainage system is also delimited since the existing drainage system of the study area is functioning well. And lastly, we delimit the installation of the solar panels and production of the real structure. So this is the conceptual framework that shows the process layout of our study. So first, we gather the data for the low-impact development techniques, the solar power system, and for the proposed building. So under the low-impact development techniques, we design the green roof and pervious pavement. Then under the proposed building, we design the slab, we determine the earthquake load through the earthquake analysis, we design the structural members using LRFD such as the beams, columns, connections, and base plate, and lastly, we design the footing. So after all these activities, we came up with the final design and compute estimation and costing of the whole proposed study.
I'm Alvin C. Agustin, and we will be able to talk about Chapter 2. Chapter 2, Methodology. In this chapter, the methodology elaborates and defines the process layout of the study, as stated by the framework shown below. The purpose of this study is to give clear and organized detailed process of the execution of the activities and computation that were done during this study. Gathering of data. The researchers first conduct survey from the College of Engineering and Architectural students and some of nearby departments such as the College of Business Studies and College of Computing Studies. This survey was about their knowledge, assumption, and opinion about LID and their experiences during planning in their corresponding department around DABSU. This contributed to the ideas that the researchers were developing for the study. This is the survey question, and we will give a small definition about LID. LID, or Low Impact Development, is a stormwater management treatment that introduces different techniques to mitigate excessive stormwater runoff or discharge. This survey question is answerable by yes or no. Next is the primary sources of structural designing was based on provision and specification of National Structural Code of the Philippines, or NSCP 2015, and from American Institute of Steel Construction, or AISC. And we get data from Philippine Atmospheric, Geophysical, and Astronomical Services Administration, or PAGASA, Office in Pampanga, such as infiltration and precipitation data of Pampanga Province, and other necessary detailed data for this study. These were used in designing green roofs and previous pavement. And from steel structure design, behavior emphasizing load and resistance factor, 7th edition of C. Salmon, J. Johnson, and F. Malas. For the floor plans, were provided by the Office of the Physical Plant in the school. While the resources of low impact development and solar power was based from the article and studies. Next is low impact development techniques. First technique is the green roof. Green roofs. This technique is applied to the roof deck of the building to be designed thus adding its weight to the load that the building carries. Green roofs consist of vegetation, growing medium, root barriers, drainage, insulation, and slab protection. These green roofs consists of combination of extensive and semi-extensive plant used for vegetation. These are sedum plants, Carabao grass, and moss plant for extensive, and Rubbertia plants, Achillea, Dianthus, bulb plants for semi-extensive. They were gathered this by suitability and availability in the country. Next technique is the previous pavement. Another technique from LID applied to this study is the use of pavements as driveways along the proposed building. The main materials of this pavement is the turf blocks, shown in the figure. Turf stone is a concrete grid materials, permeable pavers, ideals for driveways and parking areas. Along with this are the stone, mesh wire, and geotextile. Since there is already an existing drainage around the said area, there's no need to design the drainage system. The researchers determined the area to be designed as previous pavement. To calculate the quantities and estimated costs for this technique, they also use a 10% waste factor that they considered on estimation of the number of the blocks. Then, this is the infiltration rate table based on United States Department of Agriculture or USDA. The proposed previous pavement, they have a soil texture of gravel, sandy gravel, and this belong to hydraulic soil group A, and they have an infiltration rate of 1.63 inches per hour or 4.44 centimeter per hour. Next is solar power. Solar power is additional to the study. Solar power is designed to be installed on the roof of the Olsea building that will provide energy for the proposed building. This was designed to suffice low energy consumption appliances such as the electric fans and lights due to limited absorbing power of solar panels. The total energy consumption to be supplied by the solar power was calculated by the adding up all the quantities of appliances with their corresponding wattage. To get that, they have a formula of WT equals summation N times P, where the WT is the total consumption, power or wattage, and N equals to number of certain appliances, and P is the power rating of each appliances. The estimated total energy consumption per hour was calculated by the equation. WT or the total consumptive power or wattage times time usage hour per day, time is 30 days per month, times in 1 kilowatt divided by 1000 watts equals to appliances kilowatt hour per month consumption. The researchers sought for the availability solar panel from the market that could supply the calculated solar energy consumption of the proposed building. The estimated number of panels was also computed. The number of panels doubled considering the availability of the sun to be either side of the Olsea building roof. Next is for the proposed building. First is the design slab. Design of slab. The proposed building, one is slab. This table 3 minimum thickness of non-pre-stress beam or one-way slab unless deflection are compound based on NSCP 2015. For the member, solid one-way slab for the simply supported, we use L over 20, and for the one end continuous, we use L over 24, and for both end continuous, we use L over 28. And for the cantilever, we use L over 10. And other for the beams or rib one-way slab, we use for simply supported L over 16. For one end continuous, we use L over 18.5. For both end continuous, we use L over 21. And for the cantilever, we use L over 8. For the designing of one-way slab, first, determine the thickness of the slab of one-way slab. Next is determine the superimposed load. This superimposed load is based from the provision and the specification of NSCP 2015. Next is if short span over long span is less than 0.5, therefore it is a one-way slab. Next is for the yield strength or Fy other than 415 MPa, multiply the thickness into 0.4 plus Fy over 700. Next is determine the flexure strength of the member. And then after getting the flexure strength of the member, we calculate the steel ratio in its moment using the formula. Rho equals 0.85 F prime C all over Fy times quantity 1 minus square root of 1 minus 2Ru all over 0.85 F prime C, where Ru equals Mu equals reduction factor BD squared. Then check for Rho min. Rho min equals 1.4 all over Fy. Then after that, calculate the steel area using the largest steel ratio between the two steel ratio calculated above. AS equals Rho BD. After we calculate the steel ratio, determine the number of bars to supply by dividing the total area to the area of a single bar. After we get the total number of bars, for that, we get the spacing. Spacing is required at this time, which S equals number of bars all over 1,000, round up to the nearest hundreds. And check the condition of spacing. S equals 5T nor 450 millimeter. Then for the proposed building, after one-way slab, we calculate the two-way slab. First, from the ACI coefficient method. First, if short span over long span is greater than 0.5, we consider two-way slab. Then determine the slab thickness. Formula of thickness equals perimeter times 1,000 divided by 180. Then round up to the nearest number divided by 25 millimeter. Divisible by 25 millimeter. Then calculate the loadings in terms of uniform load or kilonewton. Next is calculate the area. If the area is greater than or equal or 7.5 millimeter squared, reduce the live load by LR equals LL times 0.25 plus 4.75 all over square root of AI. Then after that, determine the ACI coefficient in the table below. Interpolate if the ratio of the short span and long does not met to the given coefficient in its ratio. Then calculate the moment for the column strip or middle strip. For the moment positive equals 1.2 coefficient dead load times weight of dead load and short LA squared plus 1.61 coefficient live load times weight of live load and the length of short span squared for the middle strip. And for the column strip continuous ends, moment negative equals negative coefficient times W times LA squared. And for the column strip, discontinuous ends, M negative equals moment positive, the all over 3. Then, after getting that, calculate the still ratio of each moment using the formula. Rho equals 0.85 F prime C over Fy times quantity 1 minus square root of 1 minus 2RU all over 0.85 F prime C. Where RU equals mu all over reduction factor BD squared. After getting the still ratio, after that, check for rho min equals 1.4 all over Fy. Then, calculate the still area using the largest still ratio between the two still ratio calculated above. AS equals rho BD. Then, after we get the still area, determine the number of bars to supply by dividing the total area to the area of the single bar. After we get the total number of bars, we get the spacing. Spacing is required as this time. Spacing equals number of bars all over 1,000, round up of the nearest hundreds. Then, check the condition of the spacing S equals 5T nor 450 millimeter. This is the moment coefficient method that we use.
For the design of beams, we will get the loads. Next is the ultimate moment required. And then after all of that, we must choose a steel section. By trial section, we will get the desired section, steel section in the ASEP manual or ASEP book, or the book of the Association of the Structural Engineering of the Philippines. And then next, add the weight of the section. And after adding the weight of the section, we must check for the compactness. For the compact, we have the formula lambda must be less than or equal to lambda p, and the nominal moment is equals to plastic moment. For the non-compact, it must be lambda is equals to lambda r, where nominal moment is equals to mr, and mr is equals to quantity Fy minus Fr quantity multiplied by S. For partially compact, it must be lambda r greater than lambda, and lambda must be greater than lambda b. For nominal moment, it must be equal to plastic moment minus quantity plastic moment minus moment r quantity, and then multiply to the quantity lambda minus lambda p over lambda r minus lambda p. Quantity, it must be less than or equal to plastic moment. And after all of that, we must check the force shear and check for deflection using the grass. And for the proposed building, for the design of columns, we must first factor all the load or factor load PU, and then we must assume the section, and then we must calculate the critical stress, and after that, we must calculate the area gross, which is equals to PU over PC multiplied by FCR. And then for the design strength, PC multiplied by PN is equals to PC multiplied by FCR multiplied by AG. And then we must check it by if PC multiplied by PN is greater than or equal to PU. And then for the design of the connections, design strength based on spacing and edge distance. First, we must calculate the PU, which is equals to VPN, and the hole center must be greater than 3D. And the last one, distance from the center of any standard holes to the end must be greater than 1.5D. We have the formula for TU, which is equals to VAN multiplied by Fy, and Ft is equals to Fy. Pu, or the ultimate load, is equals to ultimate factor load is equals to Vpn. For the base plate, for the design of the base plate, we must calculate the Mu and Pu, and then we choose the section, and then we must determine the eccentrically applied load and the eccentrically critical applied load, where eccentrically applied load, or E, is equals to Mu over Pu, where the E critical is equals to N over 2 minus Pu over 2Q max. For the determining the bearing length Y is equals to N minus 2E, where verifying the pressure Q is equals to Pu over Y. For the plate thickness, solving of plate thickness at bearing interface, which is TP required, is equals to 1.5 m multiplied by Fp over Fy. It is equals to 1.5 n multiplied by Fp quantity square root of Fp over Fy. And then after all of that, we must determine the anchor rod size, and then the number of bars for pedestal, which is N is equals to AS over AB. Next is the designing of the footing. For the isolated footing, first we must calculate the area of the footing, which is equals to unfactored load over the soil bearing capacity, or QA. And for the solving of the QE, or the effective soil bearing capacity, it is equals to QA, or the soil bearing capacity, minus the summation of unit weight multiplied by height. And then after all of that, we must calculate the area of the footing, or the effective area of the footing, which is equals to unfactored load over the effective soil bearing capacity. For the square footing, it is equals to L squared. And then we must calculate the ultimate soil bearing capacity, which is equals to factored load over the area of the footing. And then we check or calculate the effective depth by punching shear or Y-beam shear, and then we can calculate the number of bars. For the combined footing, first we must locate the point of the application. So how? We can get the point of the application by the formula Pxg, which is the center of gravity, which is equals to P1x1 plus P2x2. Solve for L. By xg, it is equals to L over 2. For the D, or the total depth, it is equals to D, or the effective depth, plus 0.5 multiplied by diameter bars plus concrete cover. And then after that, we calculate the effective soil bearing capacity by effective soil bearing capacity. It is equals to QA, or the soil bearing capacity, minus unit weight of concrete multiplied by height of the concrete minus unit weight of soil multiplied by height of the soil. And then we calculate the area of the footing, which is equals to P over the soil bearing capacity. And then we can calculate the base of the footing, which is equals to area of the footing over L. By calculating the effective soil pressure, or QU, we can calculate it by QU is equals to PU over area of the footing. And then we can get we can check if it is okay by punching shear or by beam shear. And then we can get the main bars and the development length.
For the green roof, these are the design for the green roof. First is the vegetation. Second is the growing medium. Next is for the filter layer. And next is the drainage layer. Next is the roof protection layer. And next is the waterproofing membrane. For the materials, we need a 385 square meter of vegetations. For the growing medium, we need a 49 cubic meter. And for the drainage, we need a 1,540 pieces. For the root barrier, with the dimension of 30 inches by 25 feet, we need a 64 pieces. And for the insulation, with the dimension of 1.2 by 2.3 meters, we need a 140 pieces. For the slab protections, we need a 9 4-liter can. And next is low, in, for low impact development, another technique, pervious pavement. This is the data we gathered from Pagasa. And the material will be used is turf stone with the dimension of 0.6 meters by 0.4 meters by 0.01 meters. We need 2,469 pieces. For the gravel, we need 118.49 cubic meters. And for the geotextile, we need 1,767.03 square foot. And for the exfiltration pipe, we need 20 pieces. For the welded mesh wire, we need 1,767.034 square foot. And for the edge restraint, we need 731 feet. Next is the solar panel system. These are the design for the solar power system. And the materials will be used is fluorescent light bulb and ceiling fan. For the fluorescent light bulb, with 105 pieces with 16 watts, total of 1,680 watts, and ceiling fan with 40 pieces and 75 watts. And the total of watts is 3,000 watts. The total loads for the building is 4,680 watts that will be supplied by the solar panel system. Next is the specification for the solar system. 5 kilowatts solar power installation and labor package with 5 kilowatts capacity and quantity of 2 sets. For the designing of building will be discussed by Evangelista Alvin Jojo P.
I'm Alvin Evangelista and I'll be discussing about the design of the proposed building. First is the design of the slab. For the roof deck, we'll be using a thickness of 150 mm, and for the number of 16 mm diameter bars for the short span, discontinuous, we'll be using 3 pieces spaced at 300 mm on center located at the top. For the middle, we'll be using 4 pieces spaced at 250 mm on center located at the bottom. For continuous, we'll be using 9 pieces spaced at 100 mm on center located at the top. For the long span discontinuous, we'll be using 2 pieces spaced at 500 mm on center located at the top. For the middle, we'll be using 3 pieces spaced at 300 mm on center located at the bottom. For continuous, we'll be using 4 pieces spaced at 250 mm on center located at the top. For the second floor and the third floor, we'll be using a thickness of 150 mm and the number of 16 mm diameter bars. For the short span discontinuous will be 3 pieces spaced at 300 mm on center located at the top. For the middle, we'll be using 3 pieces spaced at 300 mm on center located at the bottom. For the continuous, we'll be using 2 pieces spaced at 300 mm on center located at the top. For the long span discontinuous, we'll be using 2 pieces spaced at 500 mm on center located at the top. For the middle, we'll be using 2 pieces spaced at 500 mm on center located at the bottom. For the continuous, we'll be using 3 pieces spaced at 300 mm on center located at the top. Next is the earthquake analysis. In the figure shown, it shows the girder moment, girder shear, column moment, and column shear of each member of the longitudinal section. It also shows the base shear distribution. The next figure shows the girder moment, girder shear, column moment, and column shear of each member in the transverse section, and it also shows the base shear distribution for the transverse section. The next is the design of the beams. For the roof deck, we use W8 by 40 for the longitudinal section and W12 by 45 for the transverse section. For the third floor, we use W10 by 49 for the longitudinal section and W12 by 50 for the transverse section. For the second floor, we use W12 by 50 for the longitudinal and W12 by 58 for the transverse. This is an example of the computation for the beams. We have a given reduction factor that is 0.9, Fy that is 248.4 megapascals, and Mu that is equal to 252.191 kilonewton meter. To find the plastic modulus, we use 252.191 times 10 raised to 6 Newton millimeter all over 0.9 times 248.4 Newton over millimeter square. And the answer is 1128.068527 millimeter cube. Next, we use the trial section W12 by 50 to get Mu actual and Mu capacity, where Mu actual must be less than or equal to Mu capacity, and Mu capacity is equals to 254.301 kilonewton meter, and the Mu capacity is equals to 0.9 times 1186 times 10 raised to 6 times 248.4, that is 264.938 kilonewton millimeter. Since Mu actual is less than Mu capacity, therefore it is safe. To check for the compactness of the beam, we can use lambda that is equals to Bf over 2Tf, that is 6.31, and lambda p that is equals to 65 over square root of 36, that is 10.833. Since lambda is less than lambda p, it is compact. We can also use d over tw must be less than or equal to 640 over square root of Fy. D over tw is equals to 32.994, and 640 over square root of Fy is equals to 106.67. Since d over tw is lesser, it is compact. Therefore, we can add up W12 by 50. To check for the shear strength for the longitudinal and transverse, reduction factor Vn must be greater than or equal to Vu. Since for the longitudinal, reduction factor Vn is equals to 22.042 kilonewton and Vu is equals to 109.49 kilonewton, therefore it is safe. For the transverse, reduction factor Vn is equals to 316.309 kilonewton and Vu is equals to 177.896 kilonewton, therefore it is safe. To check for the deflection for the longitudinal and transverse, the allowable deflection must be greater or equal to the actual deflection. The actual deflection for longitudinal is equals to 3.05, and the allowable is equals to 16.67. Therefore, it is safe. For the transverse, the actual deflection is equals to 6.61 millimeter, and the allowable deflection is 19.44. Therefore, it is safe. For the design of the tie beam, we use the dimension 500 mm by 250 mm with a compression bar of 2 pieces, 28 mm diameter bars, and for the tension, 6 pieces, 28 mm diameter bars. The spacing for stirrups is 300 mm. For the columns, since all columns are designed with the same type of section, they can all be considered as 1. So we can use W12 by 65. The design of the column pedestal, let's try 400 by 400 mm, where AST is equals to 0.01 times 400 squared is equals to 1600 millimeters. For the number of bars, for 20 millimeter diameter, divide 1600 over pi over 4 times 20 square, that is equals to 5.1 or equals to 6 pieces. For the clear spacing, 400 equals to 80 plus 20 plus 2 times 20 plus x, where x is equals to 260 millimeters, that is less than 1.5 the diameter of the bars, that is equals to 30 mm, and less than, and must be less than 40 mm. For the lateral ties, S is equals to 16 dB, that is 6 times 20 equals 320 or 350 mm. Number 2, S is equals to 400 dt or 48 times 10, that is equals to 480 mm or equal to 450 mm. Last is S is equals to 400. So therefore we will use 350 mm on center. For the column pedestal, we use, for the weight of the column, we multiply 23.54 by 0.4 by 0.4, that is equals to 3.77. For the PU actual, it is equals to 685.44 plus 3.77 times 1.3, that is equals to 690.341 kilonewtons. For checking, the area of steel is equals to 1,884.956 millimeters squared, and the gross area is equals to 160,000 millimeters squared. To get the raw area of steel over area gross, that is equals to 0.01178. To get the PU capacity, that is equals to 0.65 times 0.8 times 0.85 times 0.20 times 28 times 16,000 minus 1,884.956 plus 415 times 1,884.956. That is 2,363.605 kilonewtons, where PU capacity is greater than PU actual, so therefore it is safe. For the design of columns, the dimension for the column is 400 by 400 millimeters, and the number of bars is 6 pieces of 20 millimeter diameter bars. And the spacing of the lateral ties is 350 millimeters. For the design of connections, for the specification, we use A 325 volts, and the dimension is 7/8 inch, and the quantity is 8 pieces, where 4 per row. For the solution of the connection, we have a given diameter of bolts, that is 7/8 inches, that is equals to 22.225 millimeters, and PU actual, that is 251.95 kilonewtons or 56.641 kips. With the given factor load PU, compute the design shear strength theta reduction factor Rn for fasteners subject to shear alone. That is 0.75 times 0.5 times 120 times 1 times 0.6013, where it is equals to 27.1 kips or 120.545 kilonewton. Next, the design tension strength the reduction factor Rn for fasteners subject to tension alone. That is 0.75 times 0.75 times 120 times 0.6013, that is equals to 40.6 kips or 180.598 kilonewton. Compute the number of fasteners per line, where M is equals to 56.641 times N all over 2, that is 226.564 inches kips. N is equals to square root of 6 times 226.564 all over 40.6 times 3, that is 3.3 required for M alone. For N is equals to P over 2R, that is 56.641 all over 2 times 27.1, that is 1.05 required for shear alone. For the number 4, try a number of bolts to be used. Try 4 bolts per line. That is, summation of y squared equals 4 quantity 1.5 square plus 4.5 square equals 90 inches squared. RUT is equals to mu times y all over summation of y squared must be less than or equal to reduction factor R and T. RUT is equals to 56.641 times 8 times 4.5 all over 90, that is 22.656 kips, that is less than 40.6 kips, where that is okay. RUV is equals to PU over summation of N must be less than or equal to reduction factor R and P, that is equals to 56.641 over 8, that is 0.08 kips, that is less than 27.1 kips, that is okay. Check the interaction between shear and tension from LRFD table J35. Reduction factor F prime UT is equals to 0.75 quantity 117 minus 1.5 of FUV must be less than or equal to 0.75 times 90. Reduction factor F prime UT is FUT AB is equals to 87.75 times 0.06013 minus 1.13 of RUV must be less than or equal to 67.5 times 0.6013, that is equals to 40.6 kips. 52.764 minus 1.13 of by 7.08, that is equals to 44.76 kips, that is greater than 22.656 kips. That is okay. So therefore, use 8 pieces of 7 over 8 inch diameter, 325 volts, 4 per row. For the design of the base plate, the materials used is base plate with the specification of ASTM A36, size of 13 over 16 inch by 16 inch by 8 inch. And for the anchor rods with the specification of ASTM F1554 grade 36, the size of 3/4 inch diameter and 12 inch in length, with a quantity of 4 pieces. To design the base plate, compute the required strength PU and MU. PU is equals to 685.44 kilonewton and MU is equals to 44.81 kilonewton meter. Choose the trial base plate size. Try N equals to 393 mm and B is equals to 191 mm. Determine E and E critical. E is equals to 44.81 all over 685.44 equals 65 mm, and FP max is equals to reduction factor times 0.85 times F prime C times square root of A2 over A1 equals 0.65 times 0.85 times 28 times 1, that is 15.47 MPa. For the Q max, it is equals to FP max times B equals 15.47 times 191, that is 2,954.8 Newton over meter. The E critical is equals to N over 2 minus PU over 2Q max equals 393 over 2 minus 685.44 times 3 all over 2 times 2,954.8, that is equals to 80.5 millimeters. Therefore, E is less than E critical, and the design meets the criteria for the case of a base plate with small moment. Next is determine the bearing length, Y. Y is equals to N minus 2E, that's equals to 393 minus 2 times 65. So Y is equals to 263 millimeters. Verifying the bearing pressure, Q is equals to PU over Y, that is equals to 685.44 minus 263 equals 2.61 kilonewton over millimeter. Determine the minimum plate thickness. At the bearing interface, M is equals to 9 minus 0.95D all over 2, that is equal to 393 minus 0.95 times 302.51 all over 2. That is M is equals to 52.81 millimeters. FP is equals to PU over BY, that is 685.44 times 10 raised to 3 all over 191 times 263, and that is 13.645 megapascals. Since Y is greater than or equal to M, the TP required is equals to 1.5 meters of square root of FP over FY, that is 1.5 times 52.81 square root of 13.645 over 250. TP required now is equals to 18.51 millimeters. Check the thickness using value of N. N is equals to B minus 0.8 of BF all over 2, that is 191 minus 0.8 of 100.84 all over 2 equals to 55.164 mm. The TP required is equals to 1.5 square root of FP over FY, that is 1.5 times 55.164 times square root of 13.645 all over 250, that is 19.33 millimeters. Now use a base plate of 13 over 16 inches by 16 inches by 8 inches. Determine the anchor rod size. Since no anchor rod forces exist, the anchor rod size can be determined based on the AISC guide or guide, OSHA requirements, and practical consideration. Use 4 3/4 inches diameter rods, ASTM F1554 grade 36 with a length of 12 inches. Therefore, we adopt 13 over 16 inch by 16 inch by 8 inch ASTM A36 base plate and 4 3/4 inches diameter rods, that is ASTM F1554 grade 36 12 inches rod length. Next is the design of the footing. We have used two types of footing. First is the isolated footing with a dimension of 4 meters by 4 meters with a depth of 420 with a number of bars of 16 pieces of 20 mm diameter bars both ways, and a combined footing with a dimension of 7.5 meters by 4 meters with a depth of 435 millimeters with the 16 pieces of 20 mm diameter bars along its long span and 16 mm temperature bars spaced at 200 mm and 3 pieces of 20 mm diameter bars for the columns.
For the green roof, the material, vegetations. We need a 385 meters squared of vegetations. Cost of 1,000 per meter squared with a total of 385,000. Growing medium. We need a 49 cubic meters of growing medium. Cost of 500 per cubic meters. and total amount is 24,500. For the drainage, we need 1,540 pieces with the cost of 158.15 per piece, total of 243,551. For the root barrier, we need 64 pieces, cost of 1,820, total of 116,480. And for the insulation, we need 140 pieces, cost of 1,200. Total amount of 168,000. For the slab protection, we did 9 pieces can and cost of 790 per 4 liters, and total amount of 7,110. For the total cost, 944,641. And for the cost benefit, for the summary of benefit cost analysis result, considering the span of 20 years, total cost is 1,066,741. For the conventional roof is 582,200. And the total benefits is, for the green roof is 2,708,994.52. And the net benefit is 1,642,253.52. And the benefit cost ratio is 1.56, greater than 1 and less than by 2, and it's okay to implement. For the benefit cost analysis of pervious pavement, with a span of 25 years, total cost is 846,897.37. For the concrete pavement or conventional is 898,824.89 with a span of 25 years. The total benefit cost is 1,043,150.58. The net benefit is 196,203.24. And the benefit cost ratio is 0.23, even though it's less than by 1. We can implement pervious pavement because of the benefit, or you can save after 25 years. And for the costing of solar panel or solar power system, we need a 5 kilowatt solar power installation and labor package with capacity of 5 kilowatts, 2 sets, or with 2 set, cost per set is 450,000, total amount of 900,000. And the comparison between non-renewable source to solar power system with span of 25 years. Non-renewable PELCO, with a in span of 25 years, 3,816,72 pesos. For the solar power system, it's only 900,000. Total amount saved is 2,916,72 pesos for 25 years. And the summary for the solar power system is estimated material cost is 900,000, and total load can supply is 10,000 watts or 10 kilowatts. And for the chapter 4, summary and conclusion and recommendation will be discussed by Alex Bantimano.
So for chapter 4, summary, conclusions, and recommendations, this chapter explains the results of the researchers' general and specific objectives, and they are as follows. So first, low impact development. Low impact development is a method to treat excess stormwater runoff in the area. Considering the characteristics of LID techniques is the first thing considered, and the rest thing will follow. So in the case of the researchers only used 2 techniques because it is the only applicable to the site location or the area, which is the College of Engineering and Architecture main building or College of Engineering and Architecture extension building for their proposed 3-story building. The only two characteristics or the only two techniques the researchers considered are the green roof and the pervious pavement. Next is the solar power system. Solar power system is a method of the researchers to lessen the usage of non-renewable energy, which is the most convenient or the most widely used sources of energy, and the non-renewable energy, as we all know, emits more carbon dioxide that harms our environment. Solar power system also concerned in the study of the researchers, what I've said, computing the total load of the supply or computing the total load to supply is the first to consider, and as we asked the different manufacturers of the solar power system, we came up to the output or the actual solar power system, which was stated in the chapter 3 and the other chapters. We are not particularly complexing our solar power system because it is not the it does not scope or it is not the scope of the civil engineering department. It's just that the researchers only use the solar power system for them to have a more alternatives in using non-renewable energy. So, for the summary of the load and resistance factor design method, since the researchers want to design a lightweight infrastructure or lightweight building, the researchers use a material which is the steel, and in order for the design of the steel, load and resistance factor design method is the best thing or the best choice in designing the lightweight building or the steel structure. So the LRFD is the most widely used method, and it has two methods in designing a steel building or steel infrastructure. These are the ASD or alternate strength design method and the load and resistance factor design method. The only differs from the two is load and resistance factor design method has a load combinations contrary to the ASD or alternate strength design method. So the researchers use a software graphical rapid analysis of structures program or GRAS to determine the maximum moment, maximum shear that will eventually use in the design process of the building. In order for the researchers to solve the steel members or the steel elements required by the researchers, they used a program in Microsoft Excel, and that will make an ease for them to solve the appropriate steel members or elements in the structure. So during the computations, the researchers found out that the most critical section is near the center of the building, particularly the framing F3 and the framing FF, solved and presented by the previous researcher. There's the researchers, as we expected, the researchers only focus on the critical section or the critical frame because if the researchers consider the critical section, it shows that the other members not critical is safe already because the researchers used the critical or the researchers consider the critical framing. So next one, for the conclusions, this conclusion answers the general and specific objectives, um, the general and specific objectives of the research. So first, the general objective, to design a lightweight building with high aesthetic and recreational value with adaptation of low-impact development. So the researchers successfully designed a lightweight three-story building. The method used by the researchers, what I have said, is the load and resistance factor design method. But in their design, or in the researchers' design, it shows and it concludes that their research or their project has a high aesthetic and recreational value and adopts two techniques of low impact development, which are the green roof and the pervious pavement, that will benefit the university, the students, and the environment. For the specific objectives, first, to design a building load and resistance factor design method. So the researchers use the load and resistance factor design method because of its efficiency in designing light material, particularly in terms of steel structure. Comparing to other methods where pertaining to ASD or alternate strength design method and LRFD, LRFD gives the more significant effect in terms of economical value and safety value. So many countries are using LRFD, and LRFD is the commonly used in other country, and some part of our country are already using LRFD. Okay. For the second specific objective, to reduce surface runoff through low impact development using green roof and pervious pavement. So the researchers conducted the survey, and in the survey shows that most of the respondents have no idea about low impact development. Most of the respondents came from the College of Engineering and Architecture and College of Business Studies and Computing Studies. The researchers chose the College of Business Studies and Computing Studies because they are nearby the College of Engineering and Architecture. So in the survey shows, as we have said earlier, the respondents have no idea about low impact development. That's why the researchers are more eager to introduce the low impact development. So in our specific objective, the low impact development techniques used by the researchers are green roof and pervious pavement. So it shows that the two techniques will reduce the surface runoff on the study area, and it will serve as the benchmark for the other university or other college to adopt different techniques or these techniques in their respective area. Next, for the third conclusion or the third specific objective, the researchers want to reduce the usage of non-renewable energy resources by installing solar power system. So as we all know, non-renewable energy came from the non-renewable source such as the fossil fuel. Since it is non-renewable, it will not propagate itself, and it will eventually diminish or be lost in existence. So the researchers, one of its alternative is the usage of solar power system. By that means, the community or the school will diminish or lessen the usage of non-renewable energy, and since the non-renewable energy in its production emits more carbon dioxide, it will affect the natural environment. So by the solar power system, it will lessen the use of non-renewable energy, and it will serve as nature friendly to the community or the university. So by analyzation, after the researchers conduct an analysis regarding the comparison, the researchers compared the non-renewable energy and the renewable energy. It shows that the university or the respective organization will benefit to the renewable energy rather than the non-renewable energy, plus the effect to the environment. After all the researchers' studies, computations, and others, researchers came up to the 3 recommendations for the future researchers. These are: widen the area to adopt more low-impact development techniques. So the researchers encourage future researchers to adopt more techniques of low-impact development by widening the area they consider. Next one, use a software like STAAD Pro or ETABS in designing a structure. So as we all know, as what I have said, the researchers only use a program on Microsoft Excel in designing their required or their desired steel members such as beams, columns, and others. So to the future researchers, the researchers encourage to the future researchers to use a software for them also to have an ease in design process. Next, design more complex procedure in solar power system to entirely supply the electricity usage of the entire building. So as the researchers only focus or only calculate the total loads required in the building for the electric fans and light bulbs and nothing more. So the researchers want the future researchers to widen a more complex or detailed calculation for the solar power system. For the entire building will supply or only using solar power system and not the non-renewable energy that will devastate the natural environment. So the recommendations recommends by the researchers, the future researchers, are widen the area to adopt more complex or more low-impact development techniques, use a software like ETABS or STAAD Pro in design structure, and to design more complex procedure in the solar power system for the entire building for design more complex procedure in solar power system to entirely supply the electricity usage of the entire building. So that ends the deliberations of our study.